Good morning. My name is Mr. Yeem, and I'm taking you for a HDL lesson today on dynamics. In particular, we'll talk about free body diagrams. But first, a quick note about note-taking. Please don't copy everything. There's too much to copy. Instead, watch the video carefully and try and understand what's going on. If there are key ideas that I'd like you to copy down, you'll be notified using this icon. Okay, so keep a lookout for it. Okay, so in the last few lessons, you've been talking about kinematics, right? You've been learning kinematics, where you've described an object's motion using its displacement, its velocity, and its acceleration. How far it's gone, how fast it's going, and whether it's going faster or slower. All these help to answer the question, how is an object moving? Okay? But the question that kinematics cannot answer is, why is the object moving? What's causing the object to travel faster? What caused the object to move in the first place from rest? So all these can be answered in this chapter called dynamics, which concerns itself with why is the object moving. Okay. Good place to start would be to think about this morning. You've made a few things move this morning from rest, right? You pulled the blanket off the bed, you've pushed your bedroom door open, and you probably pulled open your refrigerator door as well to see what's inside for breakfast. In physics words, we say that you've exerted a force. You've pulled or pushed on an object and caused it to move. In fact, we can go further. Initially, all these objects were at rest. But after applying a force, you've caused them to move. So they were no longer at rest. They were moving. They had a non-zero velocity. Now, when you have a change in velocity, we say that you've caused the object to accelerate. Okay? And this acceleration is the result of a force. Forces cause things to accelerate. And this really summarizes dynamics quite well. We'll revisit this idea time and time again throughout this chapter. Okay, but let's first go back to this pulling and pushing business, right? So when you pull an object, you exert a force towards you, and when you push an object, you push it away from you. You exert a force away from you. So this means that forces must have some sort of direction. You can also push an object really gently, or you can push it really hard. So there's some sort of idea of a strength or a degree, or in other words, a magnitude. So what quantities have both magnitude and direction? Well, vectors. Forces are vectors. And if you've paid attention to Mr. Ng's classes, you might remember that vectors are best represented with arrows, right? So when we represent vectors using arrows, its length gives us the magnitude, right? The length gives us the magnitude, and the direction of the arrow gives us the direction of the force. Direction of arrow gives the direction of force. What if an object has multiple forces? You then want to illustrate all the forces, all the magnitudes, and all the directions of all the forces that are acting on the object, right? So we can show all the forces acting on a particular object using this thing called a free body diagram. And here is an example of a free body diagram. So notice here that we represent objects using dots. We're not concerned with how the object looks like. Okay? We're going to represent it with a dot. And then we will illustrate all the forces that are acting on it using these arrows. Again, the length represents the magnitude. Sorry, I misspelled magnitude here. The magnitude. And also the direction. Okay? Now, by the end of this lesson, you'll be able to draw free body diagrams for any object that experiences these common forces: the weight, the normal contact force, the tension, and the friction. And we'll go through all of these forces in the next few examples. So in the next few examples, right, there'll be a cartoon on the left, which is here, okay? And there'll be a free body diagram on the right. So when we start a new problem, I'd like you to copy copy both the cartoon and the free body diagram, the dot, okay? And then draw in the forces with me as we go along these problems. So let's start with the first problem. The first problem is probably quite familiar to you. It's a laptop on the table. So here we've got a laptop on the table, right? Um, if you look at your laptop right now, is it moving? It's probably not moving. I hope it's not moving, right? So it's at rest. So its velocity is 0 and its acceleration is 0 as well. But there are in fact forces that are acting on your laptop. What forces are there? The first one is what we call weight. Okay, the weight. So we've now known since we were 3 that all objects fall towards the ground. To be exact, they fall towards the center of the Earth. What force causes these things to fall? It's the weight. It's a gravitational force that's exerted by the Earth on all objects. It's a long-range force. Okay, so even if you have a satellite in orbit, it is also experiencing a gravitational force towards the Earth. Now, for our everyday problems on the surface of the Earth, the weight always points downwards. Yeah, it always points downwards towards the center of the Earth. So we can draw this in our free body diagram. Okay, and there we go. But we said that your laptop wasn't accelerating downwards, right? It's not falling through your table into the ground. So there must be another force that is cancelling the effects. It's trying to counterbalance the effects. It must be pointing upwards, right? Because that's how you balance out a downwards force. So this upwards force we call the normal contact force. I'm going to draw this in here. Okay. It's called the normal contact force. Okay. Now a normal contact force is called a normal contact force because it's always perpendicular. Okay, it's always perpendicular. The normal here doesn't mean not weird. It means that it is 90 degrees or perpendicular, okay, to the surface of contact. It applies to any object that is in contact with something else. So let's say now that I put your laptop on the slope. Please don't actually do this. You might damage your laptop, right? Where is the normal where's the normal contact force acting on your laptop in this case? It's going to be perpendicular to the slope. Okay. So your normal contact force is perpendicular to the surface of contact. Okay, let's go back to our horizontal example, the safer example. Okay. So I know that it's going to be upwards, and it's going to be the same strength or the same magnitude as the weight. So I've indicated this by drawing both forces with equal length. Yeah, so equal length because equal magnitude. And they have to be equal because they're in opposite directions. And the only way to cancel each other out is for them to be equal in magnitude. Okay, so that's it. That's the free body diagram of a laptop on the table. Let's move on to the next example. So here in the next example, we've got a box on a string. It's being suspended from the ceiling, okay, by a string. Here's the box. Okay. So again, we can immediately draw in our first force. First force has to be the weight. There's a weight that's trying to pull the box downwards towards the earth. But again, the box is stationary, right? It's at rest. It's not accelerating. So this means that there must be a force going upwards. But here the box is not in contact. It's not in contact with the ceiling. So what might be providing this upwards force? Well, you might say, hey, there's a string, right? Indeed, the string is providing an upwards force. And this upwards force we call the tension. Okay? The tension is present in things like strings, in ropes, in cables, in wires. Okay? If you've ever tried to pull something with a string, you feel a force that's trying to pull you back, right? That force is called the tension. And it always acts in the direction of the string. Okay? So in this case, it's upwards. So I'm going to draw the tension force going upwards. And there again, there we have it, right? So that's all the forces that are acting on this box suspended from the ceiling. Okay, let's build on this further. So now I have a box on two strings. Yeah, it's been suspended by two strings. So what are the forces acting now? So again, I have my weight. That goes without saying. Yeah. Okay. And then I have my two tension forces. And which direction would they be in? Now remember, the tension always acts in the direction of the strings. Okay. So one is going to act this way, and the other one is going to act the other way. You can't have a string that's going, say, this way, and then have the tension going like this way. It doesn't make any sense, right? Your string wouldn't want to bend in that direction. Okay, it always wants to go along the string. Yeah? Okay, so we can then draw the free body diagram. I know I've got a weight here, and then I know that I've got two tension forces. Tension 1 going in this direction, and tension 2 going in the other direction. Okay, so that's the free body diagram for a box suspended by two strings.